this topic of topographic maps has a lot of intricacy to it. There are a lot of little details that I hope to demonstrate for you. Let's begin with the purpose. So we have been talking about the shape of the Earth. That's been our major topic. Not just the shape, but how do we measure the Earth? One of the things that we've been able to talk about is how smooth from space the Earth appears to be. In reality, as we live on the Earth, we know that it's not smooth. In our environment, there's a lot of high points and low points. So anytime we reference that about the Earth's surface, we're talking about elevation. That's measuring the vertical distance on the surface above or below sea level. So things like mountains or plateaus or plains, those are all geographic landscapes. And as landscapes, they kind of tell you a lot about the elevation. We'll come back to that actually towards the end of the year. We'll look at the topic of landscapes in more detail. But for this video, let's focus on elevation. We're basically going to be working with field maps, but instead of connecting temperature or connecting air pressure, we're working primarily with connecting elevation. So this is a topographic map. We're given a benchmark. That benchmark is the dark, bold line here. This dark, bold line is our benchmark contour. It tells us that all along this line, it's equal to 500. All topographic maps are going to communicate the same information. You have a scale at the bottom of the page that tells you how many feet or how many inches or centimeters equals a foot, mile, kilometer, whatever distance in real life. You have a contour interval, which tells you the value that each line either increases or decreases by. And as we had talked about with other maps, there's a compass. North is the top of the page, south is the bottom of the page. So using this information, we can figure out that if you travel north, you're going to encounter higher and higher elevations. Now, how would I know that? And why would I want to know that? As a hiker, if I was hiking across this map, I'd want to know, okay, what's coming up? What's ahead of me? What am I going to encounter? So if you know that these lines connect points of equal elevation, then anywhere on that first line is 520 feet, the next line's 540, the next one's 560, and the last one's 580. So on this map, we're going to look for some of that information that all maps have, like the contour interval. So we know that the value between each line is 50 meters. Next, we're going to find and use our index contour. So just like the other map, just by coincidence, we're going to use the index contour that's shown, which is 500. And we want to know what is the elevation at point Y. Now, using that elevation, that benchmark contour, that line that we have, so we know that this is 500. This next line then has to be 550. Why 550? Because that's the contour interval. And this last line, which runs through point Y, is 600. So that's how we could figure out what the elevation at Y is above sea level. Keep in mind that these lines don't really exist. This is a drawing, an artist, a cartographer who makes maps, created this by connecting points of equal elevation. Points of equal elevation that are actually measured. Someone goes out with and takes a bunch of data points, just like we did in our lab, brings them back, and they map those. And they can actually create a map from those points. All right, here's a interesting question. What is the elevation of point A? But how can we figure out that elevation at A since it doesn't sit on a line? What do you think the value would be? So because it doesn't sit on a line, we have to take a few things into account. Well, first, let's deal with what is the range it can be. So the line that's directly inside of 500 is 550. The next line is 600. Remember, we're going up by 50. That's the contour interval. And then the final circle here is 650. So now, what would be the maximum elevation at point A? Well, we know it can't be anything less than 650 because we're going up in elevation from 500 to 650. But we also know it can't be anything greater than 700 because 700 is 50 meters away from 650 meters. So if that was the case, I'd have to have a new circle drawn. So my only possible answer that would be acceptable would be any number between 651 and 699. Once again, it has to be in that range because the line right outside of point A, this line, is 650, so it can't be any less than that. Right? If I'm counting, I'm going from 600 to 650. Has to be that anything inside of here has to be greater than 650. Okay? And then I don't have another line drawn for 700, so that's where I get my range for. So if this was a test question, any answer that you gave between these two values would be completely acceptable. So one of the things that you can pick out from a topographic map is steep and gradual slopes. Now, what I mean by that is really gradient. How much does the ground change over a certain distance? So if I say something has a steep slope, that means the ground is going to increase in elevation or decrease in elevation very quickly. One way you can identify that is by calculating gradient. I'd say that's the long way. The easier way is to look for where lines are closer together. Because where lines are closer together, that's basically telling you that the ground over that distance is changing at a very fast rate. So anytime you have a very close set of lines kind of sandwiched together, that's a steep slope. And where you have lines that are far apart, then you have a flat slope. So just being able to do that is a very important part of looking at topographic maps. So let's try a few. Where is the steep slope in this map? Is it closer to A or is it closer to B? So here's my steep slope close to B. And if I go somewhere over here, that's a flatter slope. Let's try this example. Once again, what letter has the steepest slope associated with? How about this? What number has the steepest slopes associated with? The purpose of topographic maps is to demonstrate elevation. Most elevation on the Earth's surface will come in the forms of mountains or hills. So that's taking a structure that looks like this and turning it into something that looks like this. They're both the same thing. The image on the top, if it was in front of you, and the image you see on the bottom is what you would see if you were looking down. So it communicates the same information in a different way. If the lines on the topographic map are drawn and get consecutively smaller as they go in, so as the lines get to smaller and smaller circles as I get to a top, that actually looks like a mountain with its peak being in the center. So this point here is the point at the top of the mountain. They're the same thing. So topographic maps demonstrate that information by going from large circles to smaller and smaller circles, showing increasing elevation. Now, topographic maps are also going to give you bodies of water. There are really only two bodies of water to be concerned about, lakes and oceans. So in the case of a lake, it's important to recognize that lakes don't always occur at sea level. When we think of sea level, those are oceans. Lakes can be at different elevations. So in this example, we have Darien Lake. And Darien Lake is basically anywhere that it's blue. Now, unlike an ocean, which really is where we begin measuring elevation, If you were to be asked what is the elevation at the shoreline of Darien Lake, you're given this benchmark index contour line of 250. You're also being told that the contour interval is 10 feet. So that would make the shoreline where the lake meets the land equal to 240 feet. Again, that's because this line tells us what the elevation is of the land, and where the lake meets the land, that means anywhere along this shoreline, you're at an elevation of 240. When it comes to oceans, it's a different set of circumstances. Unlike Darien Lake, an ocean will always be at zero elevation, whatever it is, 0 feet, 0 kilometers, 0 meters. So if we're figuring out contour line values associated with an ocean, we're always counting up from 0. So the shoreline will be 0, and we'll use the contour interval to figure out the value of the lines. Now, in this particular situation, this map is located in the Atlantic Ocean. So that means the shoreline is 0. And if this was a test question, and you were asked to figure out what is the value of each line, like what's the contour interval from the shore all the way up to this, you would have to be able to count 0, 20, 40, 60, 80, 100. So the contour interval on this map is 20 feet. So the contour interval here is 100 meters. If I asked you what the value is of this line, it has to be equivalent to 200 meters. 0, 100, 200. This is Wolf Pond. The contour interval is 10 meters. What is the elevation of Wolf Pond? Wolf Pond has to sit at 30 meters. I want to know, what is the maximum height right here? And what is the maximum height of that island? So that means we start at 0 for the first line. We have a contour interval of 10 meters. So this would be 10, 20. So an acceptable number for this particular island would be anything between 21 and 29 meters. Another feature on topographic maps are creeks, rivers, and streams. In real life, if you've ever seen a creek, river, or stream, they flow downhill, always, 100% of the time. What that means is they start at a higher elevation and they flow to a lower elevation. So on a topographic map, rivers, creeks, and streams should always be treated as the same feature. There's really no distinction between them. In this map, you have the Newburgh River and 3 tributaries. Those are branches off the main line. There are 2 ways to figure out the direction that any river, creek, or stream flows using some information in the map. Once again, all rivers always flow from high elevations to low elevations. When we look at that same map with the Newburgh River, let's think about where the higher elevations are on our map. You can see right here, we start at 100 towards the bottom of the map, and if I follow these lines, I wind up getting closer and closer to 200. Look, there's even a 300. So the higher elevations are at the top of the map. My contour interval is 20 feet, so I'm increasing by 100. There's 120, 140, 160, 180, right? So now that we know that, the higher elevations are up here. So this is high elevation. This is low elevation. So my river should flow from high to low. So that would mean a river flow like this. The other way to determine the direction a river, creek, or stream is flowing is to use V-shaped contour lines. They'll always point upstream. So for instance, if I look at this topographic map, pay close attention to where I'm drawing the following shapes. I'm exaggerating them slightly, but I want you to see the pattern here. So Coke Creek, the white line on this map, flows across the map. We don't know if it's flowing in this direction or it's flowing in this direction. That's our job. So the method here is to look at the V's that cross through the creek. So in this example, all of these points sit at these tiny little V's. The contour lines create these V shapes. And the V's are all pointing this way. The V's point upstream. What's the opposite of upstream? Downstream. So what direction is this river flowing? It's flowing in this direction. If I needed to give it an actual compass direction, it's flowing this way. That would be northeast. So this is a foolproof way. This always works. Always works. Let's apply that same thinking to this map. We want to know what direction is Stone River flowing. Let's look for those V-shaped contour lines. Here's one. Here's another one. Here's another one. And here's another one. The V's are pointing, in most cases, in this direction. So that would make Pebble Lake the upstream part, and up here, the downstream part. And rivers flow from upstream to downstream. Stone River happens to be flowing to the northeast. What direction is Mill River flowing? These aren't really V's. They're close enough. But they're all pointing, so Mill River is flowing in this direction, which again, by coincidence, is northeast. Depression lines and Hochscher lines. So elevation is height above or below sea level. It doesn't always mean that it has to increase. There are situations where we can have a decreasing elevation. So right here it says Cedar Sink. If I'm walking from this point where I'm highlighting across, the ground is going to dip down. Now I know that because down here I have a map key that says Hochscher lines show depression. So these little dashes tell me that the ground is going in. The first Hochscher line is always going to be equal to the elevation of the recently passed contour line. That sounds really confusing. That just means if you look for the nearest contour line that you just crossed, it's going to be the same elevation. So in this case, it's 50 because I crossed 50 to get to Cedar Sink. So when I start to decrease in elevation, I start at 50. Just to review the concept of gradient, gradient was change in field value over distance, just like when we did field maps. And that formula is on page 1. I can calculate gradient between 2 points by measuring the elevation between them. So from C to D, I can measure the difference in elevation. I can use that line and the map scale to measure the distance across the ground. So I can mark off on a piece of paper my scale, and I can bring that up to my line and figure out that this has to be about 2 miles across, and then use that data to calculate the gradient. So from C to D, my gradient would be 250 feet per mile. Calculating gradient is no different in a topographic map than calculating gradient in a field. So that's a lot of information, but this video should serve as a tutorial for working with any topographic map. That's it for now. Thanks for watching.